Okay, we are going to talk about the tangent bundle uh, and its properties today. Okay, so let M be the smooth manifold. Okay. And by the way, the Lagrangian mechanics will be formulated on this tangent bundle, and then of course let P be an element on M, and then TPM be the tangent space containing the point P, where the space consists of all tangent vectors to the point P. So the tangent bundle is defined to be the union of all the points P on M, where M is the smooth manifold, such that the union of all the tangent spaces of all the M of all the P on M. Okay, so here's a visual representation of the tangent bundle. So here the manifold M here I've written as just a one-dimensional, but you could think of it, it could be high dimensional in just one. And then of course U alpha is just some open set containing P, where U alpha is a subset of M. Okay, and here is the larger space, which is the tangent bundle with the projection map or surjective map going from the higher space into M. Okay. So Tm is the tangent bundle, and then if you draw a line straight up, there's a point there that is tangent to the point P on M, and we call that vector V. And that whole line is contained the tangent space of all the vector tangent to that point P. Okay, so that's the tangent space at P. Of course, if you take the inverse projection, so pi to the minus 1 of U of alpha, then you get that portions on the tangent bundle. Okay. Now, if you have a chart, let's say chart phi of alpha, okay, so this is in coordinates representation. There will be some mapping from M onto Rn, okay. And then you can have another. Okay, so it's a mapping from U alpha containing P to Rn. Yes, so P get mapped onto phi of alpha P, and in terms of the coordinate functions, it's just x1, x2, all the way up to xn, and that is just a subset of Rn. Okay. So now we consider the domain of the domain on the tangent bundle, which is the inverse projection map of the open set U alpha. So we let U alpha hat equal to the inverse projections of U alpha. Basically, U alpha hat is a open set in the tangent bundle, and U alpha is a open set in the manifold M. Okay. Okay, now let induced chart. So this induced chart with a hat on it is a mapping from a domain in tension bundle, which is a inverse projection of U of alpha onto the R2n. Okay. The reason why it's 2n is because the manifold has a dimension m, and then the tangent bundle, so it joined with the tangent vectors. So the basis of the tangent vectors, tangent space, contain n dimensions. So therefore, the combined would be 2m as opposed to just r to the n. Okay. And so this chart here, phi of alpha hat map v, which is the tangent vector at point P, to phi hat of alpha of v. So the first part is the position of the point P, x1 all the way up to xn, and then v1 all the way up to vn are the components of the tension vectors at point P. Okay. And of course, v alpha hat here is induced charge due to the charge down at the manifold level, which is phi of alpha. Okay. So you have phi of alpha on the manifold level M that induces a chart phi of alpha hat on the tension bundle T of M. Okay. And of course, together with the induced chart and the domain for a given alpha, then we call this here an atlas for the tangent bundle TM. Okay, so next we're going to talk about the coordinate transformations at the manifold level, manifold M, and how it induces the chart on the tangent bundle. Okay, so at the coordinate transformation on the level M, you see here xi here. I can go from 1 to 3 if it's 3 dimensions or higher, and of course this here transformed to I with the prime. So that just means that this is a coordinate transformation between two systems. Okay, whether it's from rectangular to polar or polar to rectangular or some other curved linear coordinate system. Okay, so the way it induces the on the tension bundle is that you have xi, which is the point, and then vi, which is the components for the tangent velocity at that point P, get transformed. So from here to here, the first one is at the manifold level, and then the second one, the components get transformed to the new components. And this partial I prime, partial ij here, this is called the Jacobian of the map, and it's defined to be yeah. So the new component is transformed in this manner because of the coordinate transformation at the level M. Okay. So here is point P on M, So suppose this P is inside this U alpha, well, U alpha is open, and then there's another open set U beta, okay, and then of course the mapping U alpha of the intersection U alpha, the intersection of U alpha and U beta will give you a blob somewhere down here in Rn. And then you can have another chart, let's say phi beta. So this here get mapped onto another blob. Okay, so it mapped the intersection of U alpha and U beta because P is contained inside this intersection. And so you can see the coordinate transformation or the transition map between the two sides can be written as here the shaded part of the diagram is just it's a mapping only of the intersection part. Okay, so now you can have the transition map between the left to the right. So you go inverse phi alpha inverse first, and then composite that with the phi beta. Okay, so that going from left to right. So left to right is a mapping of phi of alpha of the intersection of U alpha and U beta onto phi beta of the intersection of U alpha and U beta. Okay, now going back the other way, you will do the same thing. Okay, but this time you have to go the other way. So it's going to be inverse beta, okay, composite phi alpha. So it's going to map from phi beta of the intersection of U alpha and U beta into phi alpha of the intersection of U alpha and U beta. Okay, so these are called the transition map or coordinate transformations between different systems. Okay. Okay.